Hi, my name is Erin Wood, and I will be giving an oral presentation for Table 1's experiment. Our experiment is on enzyme activity. Enzymes are proteins that act as catalysts to speed up reactions within an organism. Enzymes play an important role in organisms because they can help break down molecules for digestion, increase metabolism, and bind molecules. We are working with the enzyme trypsin. Trypsin cleaves at dietary proteins that an organism consumes. Trypsin is found in the small intestine, and it breaks down target dietary proteins by cleaving at their peptide bonds. The trypsin enzyme is usually exposed to a pH of 8. Our group wanted to question whether trypsin activity would increase as temperature increased, and eventually get denatured as temperature increased to an extent. Our hypothesis, trypsin activity in azocasein will have a gradual increase in activity between 23, 37, 48.5, 50, 63 degrees Celsius. But at 70 degrees Celsius, the enzyme activity will have a sharp decrease due to denaturement. Our rationale was that temperature increases movement, so more movement meant more activity for the enzyme, and more peptide bonds broken by the enzyme. For each of the given tubes tested at the specific temperatures described, we added 450 uniliters of the reaction buffer. Our reaction buffer included sodium chloride and trihydrochloride at a pH of 8. We also added 500 uniliters of the substrate azocasein and 50 uniliters of the enzyme trypsin. Each of the experimental tubes was incubated for 20 minutes at the desired temperature in a hot water bath. After 20 minutes, the tubes were removed from the bath and TCA was immediately added. We added 500 uniliters of TCA to stop enzymes from acting, denature macromolecules, and undigested azocasein. This paused the reaction so we could test how much of the azocasein was left and how much the trypsin had broken down. After the addition of TCA, we put the tubes in the centrifuge. We centrifuged at 1400 RPM for 2 minutes. The process of centrifuging separates the supernatant, which contains the digested product, and pellets the undigested product. The supernatant is extracted with a micropipette and then put into a clean cuvette to be put through the spectrophotometer. The spectrophotometer is set at 440 nanometers and is blanked with water. Each experimental tube is placed in the spectrometer and then the value is recorded. This is the measurement of how much of the digested protein is in the solution. The substrate azocasein was used because it has sulfamylinide added to it. Sulfamylinide covalently bonds to the peptide bonds of the milk protein casein. The color of the sulfamylinide is orange, and therefore the darker the orange color, the more the broken peptide bonds are in each reaction tube. The spectrophotometer measures the intensity of color. The more intense the color absorbance, the more enzyme activity that occurred. Our experiment had a few controls. For instance, we controlled the pH and salt concentration by using the same buffer. We chose the buffer that we did because its pH is 8, which is the same as the pH of the small intestine where trypsin is found. We also centrifuged each of the tubes the same way for the same time and treated every tube the same with the amount of substrates added. For instance, we added the same amount of trypsin, the same amount of azocasein, and the same amount of the buffer. The purpose of the replicates is to ensure accuracy. The 3 replicates for both the negative and positive controls at each temperature help make sure that we are keeping our experiment accurate and that another person, if they were to do this experiment, would get similar results and variability. Our results showed that enzyme activity did increase as temperature increased, but we are unable to prove our hypothesis since the p-values were not under 0.05. We recorded each of our test tubes for the positive and the negative controls. We had 3 for each, so we had 36 tubes overall, with half being the negative control. We then took their averages and their standard deviations. Our standard deviations were relatively low, with 23 degrees Celsius being the highest standard deviation. This may be due to mistakes such as possibly forgetting to add TCA. The highest absorbance value was at 63 degrees Celsius, with it being 0.473. After 63 degrees Celsius, then the next highest temperature was 70 degrees Celsius. This showed a sharp decrease in enzyme activity, with it dropping to 0.295. Here we have a visual representation of our standard deviations in our enzyme activity. As you can see, the standard deviation in the 23 degree Celsius range is very high, while the others are very low. This also shows the trend in data that does somewhat relate to our hypothesis of enzyme activity increasing as temperature increased. At 70 degrees Celsius, enzyme activity sharply decreased, which may hint at denaturement. Next, we looked at the p-values. The p-values all did not support our hypothesis because they were not under 0.05. The closest we got was at 37 to 48 degrees Celsius, with the p-value being 0.108. In order to have better p-values, we may need to test more temperatures and provide a wider range of data to compare against. But overall, our hypothesis was not supported. I think our experiment was properly executed. We had 3 test tubes for each of the given temperatures, and we had negative controls for each temperature. To prove our hypothesis in the future, I feel that we must have a wider range of temperatures and maybe even go further than 70 degrees to really show a drop-off in enzyme activity. Enzyme activity did increase drastically from 0.277 at 48.5 degrees Celsius to 0.46 at 50 degrees Celsius. It also showed a drop at from 63 degrees Celsius, where it was 0.473, to at 70 degrees Celsius, 0.95. Our standard deviations, excluding 23 degrees Celsius, were all under 0.06, ranging from 0.004 to 0.05. I feel that our experiment was properly set up because we used 3 experimental test tubes for each temperature, and we had negative controls. We could have used a different substrate, but azocasein was the one provided. In future experiments, our group may benefit from testing a wider range of temperatures and at more frequent intervals in order to see more of a change in enzyme activity. Some problems with our experiment could be due to mistakes while pipetting, prolonged incubation period, or the lack of TCA added after the incubation period. Problems with our experiment may be due to mistakes while micropipetting, prolonged incubation, or the lack of TCA added after the incubation period. Overall, a better design may include more organization and more ranges of temperature in order to prove our hypothesis. Overall, our results seem to prove that enzyme activity does increase as temperature increases, but we do not have a relation to our hypothesis.